All right, so I'm given a bunch of data, and I'm asked the question, can we predict happiness based on certain variables? So I'm going to create a model to try to do so. I'm going to use the general linear model. It's linear because we add all these components of it together to try to make a prediction on the outcome, y. The x values represent predictors, variables and vectors assigned weights. Those weights are the b values, the estimates of the influence of y based on the relationship of y. Then we have the best guess of y when no predictors are present. And that's our BO, the intercept. So when those are added together, we can make a prediction of y. However, there's influences that can't be accounted for within our model that may exist, and those are represented by error, the E term. So the GLM is a theoretical model for predicting real phenomena. Our data are samples chosen to represent these phenomena. So the components of our model are estimates used to make inferences about the population as a whole. So since we have multiple predictors, we're going to use the multiple regression correlation, that's MRC. Since we're following the GLM, we're going to see how the x's are related to y as a means for predicting y. And we're going to predict error by doing estimates of error for differences in the observed y and predicted y, which is, they're called residuals, and that's how we're going to estimate our error. And then as far as significance testing goes, we're going to test the null hypothesis that no relationship exists. So our model here, we have happiness ratings, and then our x's are art appreciation, music appreciation, financial satisfaction ratings. So our plot here on the left, it's y predicted over y observed, and the plot shows how far the observed y values are from the predicted y values, which is a good first look to see if we might think our model might have some issues or if we think it's a good one. So the actual values in our model, we see we first have the estimates. These are the given, each given variable's weight on predicting y, and then the standard error, the margin of error we can expect when using x's and their weights to predict the y's. And then we can create a ratio of signal over noise by taking estimates over standard error to get our t values and use these for hypothesis testing. And then we have the multiple r squared in the bottom left. That is an estimate of how much variation in y our model can account for. So when we look at the p-values, we can see that we do not have any values below 0.05, so we may make the decision to fail to reject the null hypothesis, meaning that we may not have any predictors here that are significant, which doesn't look great at first, but it may not be as bad as it seems, which we'll talk a little bit about later. But first, I'm going to talk about some of the assumptions with the GLM in relation to our model. First is that there's no specification error. Essentially, is our model linear? Do we use the x's to predict y's and not vice versa? By looking at our plot here, we can probably guess that our model is pretty linear. The data follows a straight line, and we are using those x's to predict y. And then also, we want to look at if there's any measurement error. Are the variables we're using quantitative? Which they are. If we look at the raw data, we can tell, and are they accurately measuring what they say they are, which is where reliability and validity come in. We want to make sure we're representing what we're trying to predict, otherwise our predictions won't be correct. And then we're going to talk about the well-behaved error term in detail with our model. So the first step is the assumption that there is a zero mean of the error term. So since our model is additive, non-mean may affect our prediction of what y is with no x, so our intercept value. So we want the error to be to have zero mean. And if we look at the residuals against the fitted values, the dotted gray line represents a zero mean. We can see our line dances around it a little bit, but when we calculate the mean for our estimated error, it's very near zero, so we can decide to be happy with it. So move on and say it's probably not an issue. And then homoscedasticity tells us how far the y values stray from the predicted values as the model goes on. And if we look at the square root of the absolute value of standardized residuals against the fitted values, it gives us a good indication of that distance. We can see that the lower values in our model are less frequent and closer to the line, and the higher values are more frequent and further from the line. So there may be some evidence of heteroscedasticity, which could affect how correct our confidence intervals are when we're estimating. Next is the assumption of no autocorrelation. So we want to see if there's error from one predictor that may be correlated with error from another predictor. Since we all our predictors together in this model, one way we can try to test this is seeing if the residuals are correlated with lagged versions of themselves. And that's what we do here in this plot, and we can see that none of the correlations seem to go above 0.2 in any direction. So we may assume that we don't have any significant correlations there and move on, because it may not be an issue. Then we have the assumption of no correlation between predictors and the error term, which if there was correlation, it could possibly tell us that there are excluded explanatory variables that account for the error. But when we look at the correlations between our predictors and the residuals, we see that it's near zero. So again, we can decide probably this is not an issue. It doesn't seem like there are any significant correlations there that we need to be worried about. And then last but not least, we want to assume that the error is normally distributed. So if we were to remove the predictors and the intercept from our model, we'd be left with just the error, and we want that error to be normally distributed so we can make good inferences to the population based on our model. So if we look at the standardized residuals over the theoretical quantiles, which are divisions of a normal distribution, we can see that our residuals pretty closely follow that, and they don't stray too far from this line. Also, we can see that the histogram of the residual shows that the relationship, the distribution looks pretty normal. And then the more stringent Shapiro-Wilk normality test has a null hypothesis that the error is normally distributed. And with a p-value of 0.7, we can fail to reject the null hypothesis and assume that our error is normally distributed. So all this stuff looks pretty good for the most part, but we still don't know why we don't have significant results. It could be because we have multicollinearity, or high multicollinearity. So multicollinearity is the shared variance between our predictor values, and we can see this as the white space where the x's overlap each other. So my statistical package uses type 2 sum of squares, which only accounts for the non-shared variance of our predictors in the model. So you can see how high multicollinearity would be an issue. If you look at the right set of circles, there's a small amount of variance that is accounted for from each of the x's in our model. So further, if we look at the variance inflation factor and looking at the equation, we can see the RJ squared, and that is the x's regressed on each other. And if that value goes up, our denominator goes down because it's subtracted from 1, and our overall VIF score goes up. So our art and music scores have much higher VIF scores than our financial satisfaction score. So it indicates that multicollinearity may be an issue. So something to consider if we're looking at our models here and trying to figure out what's going on. Cortina says that when there's no significant results, it could be possible that our predictors may have influence under different circumstances and will produce an effect in that way. So it's useful to look at that and consider that. So keep that in mind. Fox also says that before going into the heavy specific diagnostics for multicollinearity, it's probably useful to take another look at the theory behind which predictors you put in your model to see if there's any issue with them. And if we look at art and music, it's possible that both of those variables could be actually measuring the same thing, and that is just an overall appreciation of the arts. So we may choose to choose one of those to represent the appreciation of the arts, or we may choose to find a different predictor that is measuring the appreciation of arts. But since we have the data we have, we're going to choose to pick one to represent it. So we put music in our second model here just to look at it as a means of comparison. We see that we have a value of a p-value below 0.05. So we can choose to reject the null hypothesis in this model. What's interesting though is if we look at the multiple R squared, it's much lower. What's lower in the second model than the first, which if we just looked at the R squared in each model, we may be inclined to think that the second one's not as good of a model. But King mentions that the R squared only refers to the particular sample we use. Therefore, it's not a good estimator. So it's more useful to look at the weights. And we can see that our weight is higher in music than it is in the second model, or than it is in the first model. So we may need to rethink our model a bit in order to make it more stronger in order for us to predict the Y. So second, we're going to use a different form of the GLM to look at whether we can predict sadness as our Y value. And we're going to do so by looking at two different factors, age and education. And so we're going to see if the sadness values within the different groups and the factors are significantly different. And we're going to compare means to do so. So that means looking at the error in this model will be different. Things other than the factors themselves that cause deviation from the means within the groups is going to be our error. And then in significance testing, the null hypothesis is going to be that there's no difference between groups. So looking at the values in our model, if we take the sums of squares and divide them by the degrees of freedom for what we have in our model, it gives us the mean square values. So for age and education and the age and education interaction, these are going to represent variance between the groups, where the residuals, the mean square value, is going to represent variance within groups. So we can create this ratio of signal to noise, the variance between or the variance within, to get our F values. And then looking at our model, we see that we have a p-value of less than 0.05 for education, allowing us to reject the null hypothesis. So this may indicate that education could be a good factor to Y. So similar to MRT, we're going to look at some assumptions and diagnostics. Again, it's part of the general linear model, so it's useful. First is the independence of predictors. When we look, we can see that there were more values in the young age group than the old age group. So this introduces a bias into our model. There is a relationship between the predictors. So our estimates are not going to be as accurate. This could be a really big issue for our model, and could be it could mean that we have to rethink our model. But we're going to look at the rest too. So we include the independence of residuals for the same reason we do in MRC. And we can see that the residuals and fitted values, or residuals against fitted values, whether our line is very, very close to zero. So we can assume that our residuals are independent. And then the homogeneity of variance. We want our variance within each group to be roughly equal, so when we actually compare the groups, the difference we see is not accounted for from the variance within that group, it's actually accounted for from the difference between the two groups. So we can see the one all the way on the right seems a little bit different than the rest, but if we conduct the Levine's test for homogeneity, where the null hypothesis assumes homogeneity, we have a p-value of 0.6, but we can fail to reject the null and assume we have homogeneity. And then we have the normal error distribution assumption. Again, same reason as in MRC. And we can see that our residuals, our standardized residuals, for the most part, follow the line. But there is, it seems like there's a little bit of difference. So there could be a little bit of bias in our inferences, but it doesn't really seem that bad. And then homoscedasticity, again, for the same reason. We want to make sure that we have confidence in our predictions. And we can see that the higher the value goes, it seems there's a little bit more stray from the prediction. So this could indicate that there is maybe a little less confidence in our predictions. But on the whole, it doesn't seem like it's really that bad. It could be a lot worse. And then last but not least, the outlier influence. So we can see that there's some stray, a little bit, which may kind of affect our normality a bit, but it doesn't really seem that significant. The biggest issue is the non-independent predictors that we talked about earlier. We need those predictors to be non-related, but they seem to be related in our model. So their bias is introduced, and our predictions aren't going to be as correct. A ANOVA test is very sensitive to having that type of error in there. And so we may need to rethink our model and try to include factors that are not related in order for us to make more accurate predictions.